All right, good morning, class. So we're going to follow up with our class yesterday about the conservation of mass. So if you remember about the conservation of mass, that is stating that mass, no matter what happens in the reaction, will always be conserved. So the number of atoms in the reactants will always equal the number of atoms in the products. So today's lesson is going to be on stoichiometry, which is the study of how reactants turn into their products. So today we are going to be looking at how cookies and some M&Ms are going to be joined together to see how their reactants are going to equal their products. So if you see right here, we have two cookie doughs inside of a package. Now, the package is all part of this, right? So we have two cookie doughs, one package, and then we have 8 M&Ms inside one package here, right? So when we make our cookies, we have to make sure that we see all of the reactants inside the product. So we have to keep track of all of them. So for every packet of M&Ms, there are 8 inside of them. For every packet of cookies, we have 2. So we're going to run out of one if we need to make a cookie that has 3 M&Ms on each. The one that we run out of is called the limiting factor. That means the one that once it's done, there are no more products after that point. So if we start to put these together, we're going to start to see that there's a certain ratio we need. We need 1 cookie for every 3 M&Ms. So I've written this out here. Hopefully you can see this. So we have M&Ms have 8 plus 1 wrapper, right? Plus 2 cookies and 1 wrapper. And then we have our reactant, or our products. So our products are going to be how many wrappers we're ending up with and how many finished cookies we're going to have. Now, when you're figuring out stoichiometry and you're balancing equations, you want to have these the smallest numbers as possible. So if you have a number such as 2 over 4, you could always reduce that into 1 over 2 because it's the same ratio, right? So we want to figure out how many M&Ms are we going to need, packets of M&Ms, for every packet of cookies, and how many products are we going to end up with, right? So being that we have 2 cookies per, we can open up a pack of these M&Ms, and we'll see that we have enough M&Ms for both cookies, right? But there's a couple M&Ms left over. So that ratio isn't exactly perfect. So we have to figure out what numbers are going to fit in here, all right? So we can kind of try these out. We can see that on this side of the equation, we have 8 M&Ms. And on this side, we have 3. So there is a number that would make sense for both of those, right? If this was 3 times 3 packs of M&Ms, we'd have 24 M&Ms. And over here, if we put an 8 of these cookies, we'll see that that'll end up being 24 M&Ms as well, which evens that out. But this throws off the number of cookies now, right? Because if we put an 8 down here, now we have 8 cookies, and in our reactants, we only have 2. So we can put a number over here, right? Obviously, 2 can turn into 8 pretty easily if we have 4 of those. So if we have 4 bags of cookies, and we have 3 M&Ms, we'll see that we won't have a limiting factor because we'll have a perfect amount of ratio for each of them. Now, you're going to see that I only have a total of 6 bags of cookies, and I actually have 9 containers of M&Ms. So with that ratio, you'll see that the limiting factor is actually going to be the cookies. So we'll run out of cookies before we run out of M&Ms. So if you look at the ratios, you're going to see that the number that should go here is going to be 3 packets of M&Ms, and then the number over here is going to be 4 bags of the 2 cookies. But don't forget, we're conserving all of the mass. So we have to figure out how many wrappers are we going to end up with. So if we have 3, we multiply both the M&Ms and the wrapper by 3. So that's 3 wrappers here. And if we're going to put 4, that's going to be 4 times 2 cookies, but also 4 times 1 wrapper, which is going to be 4. So that's going to end up with a total on this side as our product as 7 wrappers. And we're going to end up with 8 cookies with 3 M&Ms each. So this is actually a very similar to the reactions for combustion, let's say of something like propane. So propane you'll see inside of a grill if you barbecue in the summer, and actually propane has the chemical C3H8. So that is propane, and if you add oxygen to propane plus something to ignite the propane, you're going to have our reactants of CO2 plus H2O. So we have propane plus oxygen, and we're going to end up with a certain amount of carbon dioxide and water. So we're trying to see what the products will look like and which one will be the limiting factor. Now, unfortunately, usually propane ends up being the thing that runs out first. Well, actually, that's not unfortunately. You wouldn't want oxygen to run out first, but we usually end up running out of propane and then the barbecue's over at that point, right? But propane is probably going to be our limiting factor because there's only a set amount of propane in a tank, and the oxygen probably won't be the limiting factor because we're not going to run out of oxygen in our environment, right? And that would mean that the products for each of these is going to equal the reactants. So there's going to be the same number of carbons on this side as this side, the same number of oxygens on this side and this side, and also the same number of hydrogens on this side and this side. So for class, let's see if you guys can figure out what those numbers will be. So the way we're going to start this off is we're going to take this step by step. First, let's look over here, and you'll see that there are 3 carbons. So let's write down total number of carbons is 3. And you'll see the total number of hydrogens on this side is 8. And the total number of oxygens is going to be 2. Now, don't forget that when we put our coefficient beforehand, this is going to multiply not just the carbons, but the carbons and the hydrogens. You can't just do one because propane is one molecule that's all together. If you want more propane, you're going to get more carbons plus more hydrogens. So on the other side of our products, we have only 1 carbon, right? But you'll see the oxygen got distributed with the carbon dioxide and the water. So we have to make sure we total up 2 oxygens plus the 1 from the water, which is going to make 3 oxygens. And you'll see there's only 2 hydrogens over here. So obviously, our reactants are not equal to our products. So our ratios are off. So we got to see how much of each of these is going to equal how much of each of these products, right? So one of the easiest ones to fix right here, you're going to see is carbon. You have 3 carbons over here, and you only have 1 over here. So we very easily could take that carbon dioxide and put a 3 in front of it, making carbon equal on each side. But that now brought the total number of oxygens to 7, because now the 2 oxygens here got multiplied by 3, making that 6, and this one over here stayed the same, so that's 7. So we now have new numbers. So we have carbons are equal, but our oxygens are not, right? So we're going to have to find the numbers that are going to make this correct. So you're going to see that our hydrogens are also not equal. So we have 8 hydrogens on this side, and we have only 2 on this side. Pretty easy fix. We could very easily now take this and make that larger by making it 4 molecules of water. 4 molecules of water will bring that hydrogen total up to 8. So now both of our carbons and both reactants and products of hydrogens are equal. So you're going to see that this has also changed our number of oxygens. So when this was only adding 1 before, this is now adding 4 on top of the already 6 over here, which makes 10 total oxygens. So only one that is not balanced is our oxygens. Now this is why I left this lone oxygen molecule last, because the lone oxygen molecule will not mess up any other atom number. So we can see we have 10 over here, we have only 2 over here. So very easily we can make this number into 10 by putting it a 5. Now there's 10 oxygens on either side, and we have 8 hydrogens on either side, and we have 3 carbons on either side. So this is exactly what happens in your barbecue. Inside your barbecue, you're going to see that there's going to be some propane, and the oxygen from the environment is going to come in. You're going to start that with the starter for the barbecue, and that's going to ignite both of those, and it's going to create products. So it's going to release energy, which is going to be conserved on this side and this side. But the energy is going to be turned into heat, which is going to cook your food. But now you're going to see that you're going to end up with reactants. And if you were interested in how much carbon dioxide and how much water you're going to create for every molecule of for propane, you're going to see that that's going to make 3 molecules of carbon dioxide and 4 molecules of water. So I'm going to give you guys a few more examples, and we could talk about specifically what is going on in each of these equations, because it's really important for you guys to know specifically what happens in nature, and these that aren't just random math problems that I'm coming up with. They're real scenarios that you're going to see in the world, from the breaking down of sugar when you eat it in your body, all the way to photosynthesis when plants are converting carbon dioxide, probably that's made from your barbecue, and is converting that back into sugars and starches and fibers that make up the plant. So I'm going to give you guys a little bit of time to work on the exercise, and then we'll regroup in a bit.